Assalamu alaikum, my dear students. I think all of you are fine. Today I am going to start another lesson for you on chapter 4, which is magnetic effect of electric current. And that's why first I write the name of the chapter, which is magnetic effect of electric current. Magnetic effect of electric current. And today our topic is how torque is produced on a rectangular coil having electric current. Okay, so we are going to find an expression of torque produced on a rectangular coil having electric current, because in the last class I discussed what amount of force is exerted on a current carrying conductor. So if we use a rectangular coil, then there's four sides and electricity passing through the four sides. If it is placed in a magnetic field, then how much force is exerted on each side and what will be the total effect? Okay, is there any torque produced or not? We'll discuss it today. Okay, so our topic is expression of torque. Expression of torque produced in a rectangular current carrying coil. Okay, that's why first I am going to draw a rectangular coil. So I draw a rectangular coil. Okay, this is a rectangular coil. Maybe it is P, Q, R, S, and electricity is flowing. Electricity is flowing through the coil like this way. Okay, so these are the opposite sides. PQ and RS on the opposite side. PS and QR are the opposite sides. So the flow of current is I. And the magnetic field passing through the coil in this direction. So uniform magnetic field, it is placed in a uniform magnetic field B. Uniform magnetic field B. Okay, and let us consider the length of the rectangular coil B L and its width is B. So you understand the points? I think you understand the points. So we will find how much force is exerted on each side, and we'll see what is the total force exerted on the coil. Okay, so please everybody draw the diagram first. And you write, so according to the diagram, according to the diagram, force exerted on the side B, on the side PQ, if PQ, the expression is I L B sin theta. I L B sin theta. Flow of current I, its length is L, and magnetic field is theta. That's why we get I L B sine. Now you see, when you feel in this direction and flow of current in this direction, but this angle is theta is 90 degree. Theta is 90 degree. That's why the force, finally we get the force F PQ is I L B. This is I L B. This is equation 1. Okay. Do you understand this point? Here I said flow of current is I, length of the rectangular coil is L, and the width of the rectangular coil is B, and it is placed in a magnetic field B perpendicularly. So the force exerted on the coil is I L B sine theta. It is according to the expression of the last class. Okay, so do you understand the point? Then please write it. Now I will find the expression of the force exerted on the side QR. Force exerted on the side QR. So I write here force exerted on the side QR F QR equals to, now again flow of current is I, and now the length of this side is B. Then you see sine of theta. Now you see flow of current and magnetic field in the same direction, so the angle is 0. Angle between I and B is 0. That's why I B sine 0. Length along the direction, angle between the length and the direction of the magnetic field. So IBB sine theta. I will write I B sine theta. It is, so finally we get if QR is I B sine 0 is 0. That's why this part is 0. So if QR is 0. So I think you have finished writing. Force exerted on the side QR is FQR IBB sine 0 degree. That is IBB sine 0 is 0. That's why FQR is 0. So there is no force exerted on the side QR. Now let us find the force exerted on RS. Force exerted on the side RS. Force exerted on the side RS. Force exerted on the side RS. BFRS. Now you see, now again flow of current is I, length is B, and magnetic field is perpendicular. I mean, now this angle was 90 degree, so this angle will be 270 degree. You understand the fact? Because that flow of current changing its direction by 180 degree. So 180 degree plus 90 degree is 270 degree. So here I write sine theta is 270 degree. Theta is 270 degree. So you write here 270 degree. So we get I and the sine 200 is -1. That's why we write here F PQ equals to minus ILB. This is equation number 3. So this part is again, we get the force exerted, how much force is exerted on the side RS. So we get here RS, F RS is minus ILB. Okay, now again force exerted on the side SP, force exerted on the side SP. So I write here SP. So if SP is IBB, now you see the direction of the angle between the direction of the length and magnetic field is 180 degree. So here I write 180 degree. There, so again if SP is IBB, side 180 is again 0, and again this is equation number 4. This is equation number 4. So we get 4 equations of FPQ, FQR, FRS and FSP. But here you see force exerted on the two sides, force exerted on the two sides QR and SP. These two are 0. QR and SP are 0. That's why I write here now force FQR equals to FSP equals to FSP equals to 0. But force FPQ and FRS are equal in magnitude but act in opposite opposite direction. We know when two equal and opposite forces at two different points on a body, when two equal and opposite forces act at two different points on a body, then they produce a torque. Opposite direction at two different points. At two different points on the coil, and they will produce torque. Now let us find how much torque is produced. How much torque is produced on the coil, on the side of the coil. I tell you, the point here you see is the rectangular coil. PQRS. So this one is PQ and this one is RS. So to equal and opposite forces, look at my hand. Here is a force in this direction, upward direction, and another force acting in downward direction. So when two equal and opposite force acting on the body, then it will produce a torque, a rotation. It will create a rotation which is called torque. Okay, so they will produce the torque. Let the torque be tau. Let the torque be tau. Let the torque be tau. We know torque is equals to 4 into perpendicular force into perpendicular distance between the forces. We consider the forces FPQ or FRS into this perpendicular distance is B. FPQ is ILB into B. So is L and B is L and B is A. I B L into B. This is the area of the coil, where A is LB, area of the coil. So finally we get torque tau equals to IBA. This is for a single coil, single turn. There is a single turn in the coil, then torque equals to IBA. Torque equals to IBA. So please write the expression up to this, and then again I will express the later on. So we get, let the torque be tau, then tau is FPQ into B, and FPQ is ILB into B, and L and B is area of the coil. That's why torque equals to IBA. This is for a single turn of a rectangular coil. Single turn of a rectangular coil. Single turn of a rectangular coil. If there are n number of turns, then what will happen? If there are n number of turns, then what will happen? So you write, if there are n number of turns in the coil, now if there are n number of turns in the coil, there are n number of turns in the coil, then torque tau equals to NIBA. You understand? And if the rectangular coil is not placed perpendicular to the magnetic field, if the coil is placed at any angle with the magnetic field, then what will be the torque? So you write, if the coil is placed, so here we get the expression of the torque for a n number of turns, and the torque is placed perpendicular to the magnetic field. If the coil is placed at an angle theta with B, then torque tau will be NIBA sin theta. And now here I can write it NIAB sin theta. Now this part, you see, NIA is called magnetic moment. This one is called magnetic moment, and we write it by M, magnetic moment. So tau equals to MB sin theta, where M is NIA, magnetic moment of the coil. Magnetic moment of the coil. And finally, we can write it in the vector form as N cross B. Tau equals to N cross B. So this one is the expression for torque produced in a rectangular coil. I think you understand the point. And after finish, please write it. And when the writing is finished, then I am going to show you a video clip, a small video clip of this expression, so you can remember all the points again. and it will be more clear to you. So you understand all the points. If you have any question, then you can write to my email address at taz_uddim@yahoo.com. Okay, you can write in this email address if you have any question. So I think in this pandemic situation, you can't go direct contact with us. That's why it's a problem. But anyway, we are trying our best to describe you all the phenomena, all the expressions, so you can understand all the facts at home. Okay. Anyway, when the pandemic is over, then if you have any more discussion, then we'll directly discuss it. So is it clear to you right now? And then after this, I am going to show you a small video clip. So here is the topic today. I am going to finish magnetic effect of electric current, and I am going to show you a small video clip of this expression too. Okay, now my dear students, I am going to show you a video clip on my lecture, magnetic effect of electric current carrying loop or a rectangular coil. So let us see how magnetic field is, torque is produced.
Torque experienced by a current loop in a uniform magnetic field. Let us consider a rectangular loop PQRS of length L and breadth B. It carries a current of I along PQRS. The loop is placed in a uniform magnetic field of induction B. Let theta be the angle between the normal to the plane of the loop and the direction of the magnetic field. Force on the arm QR, vector F1 is equal to vector I into QR cross B vector. Since the angle between I into QR and vector B is 90 degree minus theta, magnitude of the force F1 is equal to BIP sin 90 degrees minus theta. That is F.
Okay, my dear students, I want to show you the direction of another two forces. That is force exerted on the side, force exerted on the side QR in this direction, F QR, and you see the force exerted on the side PS, SP is this one is SP. So this one the force FSP. So I tell you, these are the forces. These are the four forces acting on the rectangular coil. Four forces acting on the rectangular coil. So FPQ, FRS, FQR, and FSP. So these two forces you see, FQR and FSP. The two forces FQR and FSP are equal and opposite in direction on the same line. But PQ and RS are equal and opposite, but they are acting in two different points. But the action of the force, the action line of the forces FQR and FSP are equal and opposite. That's why they will cancel each other, and actually FQR and FSP equals to 0. So only the two forces FPQ and FQR are existing in the diagram. That's why these two forces will work to produce torque on the rectangular coil.